Okay, so let's continue with our discussion of linear regression. We talked about univariate linear regression, where you have one feature and one output. And we talked about gradient descent as an iterative way of finding the best linear fit, which is a linear equation that predicts the output as a function of the feature. All right, now let's look at the case where we have multiple features and not just one, which should possibly give us a more accurate interpretation. For example, previously we only looked at the housing size and its effect on price, but there might be other factors like housing size and number of bathrooms, or housing size and some other factors may come in to influence the price of the house. Okay. So that's what we've been focusing on, just introducing this innovation where instead of just one variable, we have several variables. All right. Okay. So we'll have the model representation and gradient descent, just like we did with one variable. All right. So first we talk about the mathematics of representing a model with multiple variables or multiple features. All right. So before we had size and then price of the house, as I mentioned before. X are the input variables, the features, and the output variable is the price. M is the number of examples in the training set. X, Y here is used somewhat ambiguously. In fact, X should represent the vector of all features, and Y should represent the vector of all outputs. If we want to refer to a specific feature value and a specific output value, we should use the index I, which indexes the row of the data within the table. Right? So you can see here x of 1 equals 460. That's the first element for x. X of 2 equals 70, etc. And y of 1 is the first element in the table for y. Y of 2 is the second element. Right? So we'll consistently use this notation to indicate specific instances in our database. All right, now suppose we have some other features that may affect the price of the house. We have the size in square meters, which is important. Number of rooms, that's also important. How old the house is, that's important. Number of garages, that's also going to be important. All these factors might affect the price of the house, and not just size. Okay, so you can see that's reasonable. Now here we have y is the output variable, m is the number of examples still, xi, yi, but now xi consists of several values. Xi will be a vector, right? Here in this case, x2 is the set of x2 would be this one, the set of 1, 2, 3, 4 values. And yi is still the ith target value. All right? So we're kind of upping the game with our notation. All right. Oh, okay, so here we go. We have x1, x2. So here we're using the subscript to indicate the column. Here we have the superscript to indicate the row, and the subscript is indicating the column. Right? So this is the x1 column, x2 column, x3 column, x4 column. These are all components of a single feature. So we have a feature vector. Right? The vector will have 4 components. Right. So n is the number of features. In this case, n equals 4. Xj is the jth input variable, so it's the column. Right. So subscript indicates the column, and superscript indicates the row. All right. So we have a notation that can accommodate more than one characteristic composing a feature. So here, x1, we're representing this as a column vector. Right. So this vector indicates the 4 values that are in this row, in the first row. There we go. X of 4 similarly is the 4 values in the 4th row here. And I think that should be clear. All right, so you can spell this out. In particular, you can look at some other examples. The x with subscript 2 and superscript 1 is the second element of the first row, which you can see is 4. X subscript 4, superscript 1 is the fourth element of the first row, as you can see, which is 2. And so on. All right, now when we used univariate linear regression, we had a model that expressed the price as approximately equal to some constant plus some constant times the feature. Right? Now, the natural generalization of this is simply to add more terms for the different aspects of the feature. We're not treating these different aspects any differently from the first one. We're just allowing them to influence the output in the same way, in a linear way. And here, as we saw, that this x1, x2, x3, x4, these represent the different aspects or different features that might influence the price of the house. All right? So this would be one particular model where you predict the house price by plugging in the house size here, number of rooms here, age here, and garages here. All right. So let's make our notation more streamlined. Here is what we had for our model. We can, well, we certainly can visualize it for n greater than 2. Now, in order to make things easier, and you'll see how this works in a minute, instead of treating this constant term separately, we'll just add a feature x0 equals 1. So it's kind of like a dummy feature, but it's something that would influence each of the outputs the same. It's basically the constant influence on all of the outputs. All right? But you can see here that all that does is just adds a 1 here, and then the thetas now are treated in a consistent way. All right? So you can remember that the x0 is always equal to 1. By mathematical convention, as we've seen up to now, a single example x and the parameters theta are represented as column vectors. So in the general case with n features, we represent x in this way as a feature. Now we actually have n plus 1 components, right, because we have the x0 component. And the theta now also has n plus 1 components. Okay. In this generic case with n features, h theta, for one example, can be represented as a vector dot product. Right? Our formula is x0 times theta 0 plus x1 times theta 1, and so on. But in fact, that's the well-known dot product between two vectors. And that can be expressed either this way, or if we think of x and theta as matrices, this would be x transpose theta. Remember, x is a column vector, which is basically a n plus 1 by 1 matrix. When we transpose that matrix, it becomes a 1 by n plus 1 matrix. Right? Think about transposing this matrix, and it becomes a row matrix, a matrix with one row, and then that can be multiplied by this column vector to get a number. Or we could do it in the other direction. It really doesn't matter. So in this generic case with n features, h theta is, for one example, x can be represented as a dot product. Now we need to be able to process samples much faster than just one at a time. Right? So we can speed things up if we compress our notation and put everything together. We can put all the samples together as a matrix. Just like originally, we have a table that contains all the values. The table that contains the x values can be considered as a matrix. So then we can use matrix operations on this table. Right. So here's an example. Here we have our features and our output. So this is the table that represents the inputs or features, and this is the vector that represents the outputs. So as you can see, think of this as a matrix. It's a m by 4 matrix. Okay. So we have our matrix arrangement. Our first instance, our first feature vector is the first row, second feature vector is the second row, and so on all the way down. Now if I wanted to compute the values of H for all of these feature rows at once, I simply use a single matrix operation. Okay. So here we have the instances written out as components, right? That's just expressing the components of this feature vector explicitly, and we also have this entire column to be 1. And if we arrange our theta, our coefficient vector, as a column vector, in fact, you have h theta of x equals x theta. That means that if you multiply this matrix times this vector, you will get a column vector, and each entry in the column vector will give you the prediction of the price for the given row vector. Right? So let's look at some examples. So here we have x, and these are specific values of our feature, right? This is the constant feature, this is the square meters, and so on. So in order to get the estimated price for this first row, I would do the dot product of this with this coefficient vector. And in order to get the predicted price of the second row, I do the dot product of this with this column vector. And this is exactly the rule for matrix multiplication, right? So we'll stop there, and you can see how matrices are going to be very useful and key in the mathematical representation of multivariate linear regression. Okay, thanks for watching.